initially at rest, and it's pushed for 4 meters along a rough surface. The floor is a horizontal, and there is a constant applied force of 100 newtons along the horizontal. And if the coefficient of friction between the block and the floor is 0.325, we're asked to determine the work that's done by the applied force, the work that's done by the frictional force, the work that's done by the normal force, work done by gravity, and the total amount of work that's done on the block. And then after we find all of the work done by the individual forces, we're asked to determine the final speed of the block by using the work-energy theorem. So we can start by determining the work done by the applied force. And the work done by a constant force is just the force applied, whatever that force happens to be, the displacement times cosine of the angle, where the angle is the angle between the force and the displacement. So in this picture, there is a 100 Newton force acting to the right. The displacement of the block is to the right. So the angle between the force applied and the displacement is just 0, and my distance is 4 meters. So the work done by the applied force is 400 joules. Next, we're asked to figure out what is the work done by the frictional force. And the frictional force opposes the motion, so the angle between the frictional force and the displacement is going to be 180 degrees. But we have to actually figure out what that force is in order to calculate the work, which depends on the force applied, displacement, and cosine of the angle. So I realized that in the vertical or the y direction, that the sum of the forces would equal the mass times the acceleration, but there's no acceleration in the y direction because the block only moves along the horizontal. So if I look at my picture, I have a normal force acting up, I have the weight of the block acting down, and the weight is just mass times gravity, 196 newtons. And so the normal force plus the weight acting down, which would be negative, has to add up to 0. So the normal force in this case is 196 newtons. So now that I know what the normal force is, I can calculate the frictional force, which is just the coefficient of friction times the normal force. Coefficient of friction is 0.325 times 196, which is 63.7 newtons. So now that I know the actual value for the frictional force, I can determine the work done by friction, which is just the frictional force times the displacement, this is supposed to be delta r, times cosine of the angle. And so the force is 63.7 newtons from friction. The distance covered, or the displacement, is 4 meters, and then the angle, of course, between the force and the displacement is 180 degrees. So cosine of 180 is negative. The work done by friction is negative 254.8 joules. The work done by friction is always going to be negative because the work done by friction is hindering the motion, or the frictional force is hindering the motion, whereas here the applied force is helping the motion and the work is positive. So we have the work done by the applied force, we have the work done by friction. We're also asked to find the work done by the normal force, but the work done by the normal force is just 0 because the normal force here, which is acting up, is perpendicular to the motion, or the angle is 90 degrees. And anytime the force is perpendicular to the displacement, the work done by that force is 0. And similarly, the work done by gravity would also be 0. The normal force and the gravitational force are not actually helping it move along the horizontal direction or hindering the motion. So the net amount of work would just be the sum of the work done by all of the individual forces. So I can add 400 plus the work done by friction, negative 254.8, and I get 145.2 joules. The last part of this question asks us to find the final speed of the block, and we know that the net amount of work done by all of the forces is 145.2 joules. And according to the work-energy theorem, the net amount of work done, this is also sometimes written as a sigma here, the sum of the work done, is equal to the change in kinetic energy. And my subscripts here are a little bit off, but this is the final kinetic energy here, minus the initial kinetic energy here, where kinetic energy is 1/2 mass times the velocity squared, or the speed squared. So we know the net amount of work done by all of the forces is 145.2 joules. And this has to equal the final kinetic energy, 1/2 the mass times the final speed squared, minus the initial kinetic energy. But since the initial speed is 0, because it starts from rest, the kinetic energy initial is just 0. So this term is just 0. So I get an expression that the 145.2 joules of work has to equal 10 kilograms times v squared. I can divide both sides by 10, and then I can take the square root, and I get that the final speed of the block is 3.81 meters per second. In this continuation of the example, we think about what happens when the applied force is removed from the block after it has covered that distance of 4 meters. And the question is, how far does it travel before coming to rest? So we have our picture here of the block, and we still have our normal force that we know, and we know the weight that's acting, and we already calculated the frictional force, but the applied force has been removed. So the only force that's present here is the frictional force. So we know that it was traveling at a velocity or speed of 3.81 meters per second after it had gone the 4 meters. And we're wondering, how far is it going to travel before coming to rest? And although we could use kinematics and we could figure out the acceleration of the block, we want to focus on using this concept of work energy. So we know that the net amount of work done on the block when it covers some distance is equal to the change in kinetic energy. So the final kinetic energy minus the initial kinetic energy. So if I look at the net work done on the block, the only force in this picture that is doing work is the frictional force. And so the work done by friction has to equal the kinetic energy final, and the final speed is 0, so the final kinetic energy here is 0, minus the initial kinetic energy, which is 1/2 the mass times the speed that it had initially squared. Now we know that the work done by friction is just minus the frictional force times the displacement, where this minus sign comes out because of the cosine being cosine of 180 for friction is always going to be negative. So basically the work done by friction is always going to be minus the actual force times the displacement. And that has to equal this value that we get from 1/2 the mass times the speed squared, which is negative 145.16 joules. So if I plug in the frictional force and I get rid of the minus sign, which is in both sides of the equation, then I get the frictional force of 63.7 newtons times the displacement is equal to 145.16 joules. If I divide both sides by the frictional force, I get that the displacement is 2.28 meters. So after the applied force is removed, when it is traveling at 3.81 meters per second, it will take 2.28 meters to come to rest due to this frictional force.